From our studios in New York, this is a special edition of Charlie Rose.
During the Charlie Rose Brain series, we explored one of the most fascinating subjects in all of science, neurology, the brain. We learned how the brain controls every aspect of our mental life, such as perception, consciousness, decision-making, and creativity. Our far-ranging discussions drew on biology, genetics, psychiatry, and philosophy. We examined mental illness and cutting-edge treatments. And we met some of the finest minds in science, led by our friend and guide and co-host, Dr. Eric Kandel.
Neuroscience is capable of giving us insights into phenomena that we would not think would be in the corpus of neuroscience, like morality and economic decision-making.
So this is bridging humanity and science.
It's bridging the two things, and this is the beginning. We now have some methodologies, we have some strategies, we have some beginning insight. This is just opening up. So I think this is going to make a major impact on how people make decisions, about how we influence people to make appropriate decisions, and also for making new kinds of diagnoses and developing new kinds of therapeutics.
Tonight we look back at some of the series highlights. We begin with these simple questions. What does the brain do? What are its functions? Why does it exist? Here is how our guest answered those questions.
I think we have to ask a very fundamental question, perhaps the most fundamental question we can ever ask, and I think it's remiss that Eric hasn't asked it in his first show. But why do we and other animals have brains? It's a pretty fundamental question, because there are many species on our planet who don't have brains. So that's a fundamental question that we should all be taught on our first day of school. And if you think about that question for any length of time, it's obvious why we have a brain. We have a brain for one reason and one reason only, and that's to produce adaptable and complex movement. There's no other reason to have evolved a brain. So if you think about it, the only way we can affect the outside world is through contractions of muscles. So if you think about communication, speech, gestures, sign language, writing, they're all mediated by contracting muscles. So we need to remember that things like sensory processing, the perceptual system, memory, and cognitive processes are all important, but they can only be important to drive action or suppress future actions. There's no point laying down memories of childhood or perceiving the color of a rose if it doesn't lead you to something different with your motor system later in life. So if you think from an evolutionary point of view, there'd be no point having the thinking processes if they can't be expressed through action. So I'm really a movement chauvinist. I think to understand the brain, we have to understand movement, which is the final output.
To understand the brain, yes, we have to understand movement.
We can't look at memory or perception in isolation from action. And we can say, if you don't believe in this argument, there are many species who live very happy lives on our planet, do very well socially, but they don't need to move. So the tree is a very nice example. It doesn't require complex movement. It hasn't evolved a brain. But the clinching evidence, for those who don't believe in this view, is this animal here. This is the humble sea squirt. It's a very rudimentary animal, and it has a brain, a spinal cord, and it swims around in its juvenile life. And at some point in its life, this animal implants itself on a rock and never leaves that rock again. And the first thing it does in implanting on that rock is to digest its own brain and nervous system for food. So once it doesn't need to move, it doesn't need that brain anymore. So I think it's really, the brain is there for movement.
The human brain is born with an enormous capability for acquiring information about the outside world. Infants can acquire information almost spontaneously, not only about concrete things like objects and people, but about abstract things such as language, numbers. They're brilliant learners.
This is a famous old example of the principles of Gestalt psychology, which are the principles by which we organize information. And when you first look at this picture, it's very hard to figure out what it is. In fact, it just looks like a bunch of light and dark splotches, and you may look at it for a while and just see light and dark splotches. And that actually is the information that your eye is getting from this picture, and your brain has to figure out what to do with it. Now I can show you what you should do with it, because we've here drawn some lines on top to show you that there's a dog there. It's a Dalmatian dog, and the Dalmatian dog has these light and dark spots on it. And if we go back to the original picture now.
Unbelievable.
Isn't that unbelievable?
Yes.
That's fantastic.
Now that you've seen what it really is, now you can hold that image together and you can see how to organize it. And now normally, in our normal vision, everything seems so automatic, we don't realize that this is really what's going on all the time. Our eye gives us this light and dark information, but it doesn't come in an organized form. And the problem is light and dark can come from many different sources. It could be a light or dark spot because the fur is got black or white pigment in it, or it could be some shadow that's being cast causing it to be light or dark, or it could be the edge of the dog where the dog stops and the background starts. So this information that you're given at the level of the eye is very ambiguous, and so there's a sort of a detective problem, a problem-solving task that the brain has to deal with, which is how do you piece all these bits of information, each piece being ambiguous, how do you piece it all together into a single coherent story that tells you about what's really in the world.
Suppose with shadows, and we took a tree in the morning at full moon, full midday sun, the afternoon, and then at dusk. The tree would remain the same in our vision, even though the shadows and the light intensity would change.
Yes,
why is that?
That's one of the amazing things that vision has to do, because the brain is designed to pull out the information that's stable and important and meaningful, and to throw away the information that's sort of accidental.
Our brains are not calculators where you punch in a bunch of numbers and you get a number out at the end. Our brains are ourselves, and they incorporate what's important and how we feel, and they give you different kinds of responses. And one of the most important things for us is each other. From the moment of our birth, the most important aspect of our life is our ability to predict and affect the behavior of others. And so this is a big part of what it is to be human. And I would say that the question I would like to understand is how a biological system can do something so remarkable.
Well said. In addition to defining why our brain exists, our guest also talked about how it works. In the first episode, Tony Mavshon of New York University gave us an overview of the brain's anatomy.
What we have here is the beginning of a very brief tour of the structure of the human brain. We're looking at a computer-generated image of the left hemisphere of a human brain. Now, this brain is covered, as the human brain is, most prominently by a structure called the cerebral cortex, which is this gray mantle of tissue that's really almost all that's visible when you look at the human brain from the side. And the cerebral cortex is the main computing machinery of the brain, and it's also the part of the brain that's most highly evolved in humans compared to our ancestors in the animal kingdom. Now, we customarily divide the cerebral cortex into 4 lobes, and the 4 colors in the image here show you the 4 lobes and their positions. And the 4 lobes have many different functions, but we characteristically think of them as having a number of sort of primary functions. The occipital lobe here, shown in red at the back of the brain, is the main seat of visual function. That's a lobe which is particularly dear to my heart because it's the system of the brain that I work on. The temporal lobe, here shown in green, is involved in a number of complex functions. It's involved in higher processing of visual information. It's involved in the laying down of memories. And it's involved in the processing of information about sounds and in the conversion of information about sounds into linguistic representations and into the programs that allow us to speak and understand language. The parietal lobe, here shown in blue, is sort of the central spatial orientation organ of the brain. The parietal lobe combines information from multiple senses, including vision, hearing, and touch, and it formats motor commands, output commands, for the muscles, which allow the body to be oriented in space with respect to the stimuli in the environment. So when you navigate in the world, when you look around the world, when you decide what parts of the world to pay attention to, it's the parietal cortex which is doing the bulk of the work. Finally, in purple, here is the frontal lobe at the front of the brain. The frontal lobe is the most highly evolved part of the cortex in humans. It is the part of the brain that is probably most directly responsible for making us human. It is the part of the brain that is responsible for decisions, for actions, for many functions that are often now called executive control functions, deciding what to do, where to go, what to eat, what to say, probably more importantly, what not to do and what not to say and where not to go. And so it's the ultimate sort of seat of central control in the brain.
In a later episode, Nancy Kanwisher of MIT told us how some functions like face recognition are are localized to specific brain areas where others are not.
So right now, my face area, which is right there in my brain, is active because I'm looking at your face, and now it's off, and now it's on, and now it's off. And I know that because I've scanned myself and hundreds of other people looking at faces and objects, and you can just see it turn on and off.
The fact that face recognition has a localized function, is it because it's more difficult, more what?
That's a great question. I'd love to know which mental functions get their own private piece of real estate in the brain and which don't. So in my lab, we found a few. We found regions that are specialized for face recognition right here. I'll show you on the brain. I can show you where it is. That's the front of the brain. Right. It's looking at you. And then if we turn it upside down, so you can see the bottom of the temporal lobe right here. So on me, that's right there. Yeah. That face area is right about here in the brain. And we've also found other specialized regions. So we expected to find that face region because of the work that Eric just mentioned on people with brain damage. When they had damage in this general region, they tended to have this difficulty recognizing faces. So that wasn't too much of a surprise, although it's really fun to discover. But since then, we've found several other regions that we didn't expect in advance at all. So one is a region that responds when you look at places and landscapes. And it's right next door, a little further forward, right about there in the brain on both sides.
Okay, now let me just ask this question.
Yeah.
If, in fact, I could reach inside of somebody's brain and remove the part of the brain which recognizes landscapes, say,
Yep.
and then that person would look at a landscape,
Yes.
what would they see?
Well, we've tested such a person. Years ago, when we first discovered this place area here, I was dying to know what life would be like for somebody who didn't have that region, but it's actually on both sides of the brain, and so the chance of getting brain damage on both sides is very unlikely. But I was at a conference once, and I was walking through these rows of posters, dozens, hundreds of posters, and I saw a picture of a brain of somebody with brain damage right there on both sides. And I talked to the person whose poster it was, and I said, who is that person? I need to test them. So I tested this guy who had been an artist who painted these beautiful paintings, very tragic, and he no longer painted, no longer took joy in looking at things. Interestingly, he could see where he was going, he could recognize faces, he can read, he can get around in the world, but as he told us, he never knows where he is. He has no idea where he is in the world.
He can see it, but he can't put it in any context.
But he doesn't know where it is.
In order to solve the mysteries of the brain, modern neuroscientists rely on a wide array of technologies and approaches. These include brain scans, animal experiments, drug trials, and genetics. Some of the guests described their experiments and explained how they obtained their results.
With imaging technologies, we can actually now go inside the brain of a person that's addicted to drugs and see what areas of the brain may be disrupted that could explain why is it that a person that's addicted to drugs cannot control the urge to take the drug, even though they actually can tell you sometimes they are no longer even pleasurable anymore. They were pleasurable initially, but as they repeat the taking of the drugs, that pleasure becomes less and less, and they start to take it not to get high, but just to feel normal. So with imaging, for example, we can now look inside a human brain and see, there you have a diagram that shows this famous dopamine cell. Normally, you cannot look at them. You require an imaging technology that relies on radioactivity. And the way that you're going to be looking at how drugs increase dopamine is the following way. Normally, you have dopamine cells, releases dopamine when you take a drug, for example, and dopamine sends this message by binding to the receptors. You take a radioactive compound that actually binds exactly to the same receptors as dopamine, but can only bind when the receptors are not occupied by dopamine. So that allows you to take an image, and then you bring the subject back and you test them when they are taking a drug like cocaine. Cocaine interferes with dopamine removal from this space, and those dopamine occupies all of the receptors in such a way that when you give your radioactive compounds, the receptors are occupied, and your radioactivity no longer bind. And so you see that decrease in radioactivity, which is really a function of the fact that the drugs are increasing dopamine. So you can now use exactly this technology to go inside the brain of a person that's addicted and a person that's not addicted, and to compare their brains when you give them a drug.
Aggression is really almost as arguably as important in our society as fear is. It's responsible for war, for domestic violence, for genocide, and we really understand it much less well than we understand the neural circuitry of fear. It's highly conserved in evolution. Dogs fight, cats fight, and so the aggression is very, very fundamental and important. Now, we heard in a previous episode that critical experiments by Olds and Milner showed that if a rat stimulated a particular center in its brain, it produced a sensation of pleasure, and it would do that over and over again. And even before that, experiments by Walter Hess in Switzerland in the 40s showed that if you stimulate a different region of the brain, you can produce anger and aggression, the opposite emotion. And so that was from stimulating the hypothalamus, and he showed this remarkably in cats by putting an electrode in a specific part of the brain and firing those neurons. He made this outwardly normal, happy cat suddenly express rage, hiss, lay its ears back. Now, that's starting to tell us something about the parts of the brain that are involved in emotion, but there's a great deal of interest also in the nature-nurture question. To what extent is aggression influenced by our inheritance, and to what extent is aggressiveness influenced by our environment? And we heard in the earlier today that insects have been a very good system, and Drosophila in particular, for understanding how genes affect behavior. And so an important question that comes up is whether this insect Drosophila shows aggression. And it turns out that Drosophila do show aggression, as we can see in the movie here, showing two Drosophila grappling with each other over a food patch. And you can see them almost like sumo wrestlers shoving against each other, trying to get dominance of the food patch. Now, why is that interesting? Because Drosophila breed very rapidly and are cheap to maintain. You can screen through essentially a haystack of many, many, many mutant strains of Drosophila to try to find a needle which has a higher level of aggression than normal flies have. And the next video shows an example of a genetically hyper-aggressive fly strain. So this is sort of the genetic equivalent of the Hess experiment, where these flies have been made hyper-aggressive by a manipulation of their genes. And this promises in the future some insights into how genes control aggression. But I also think it's important not to assume that environment doesn't affect aggression in the species just because genes do. In fact, environment affects aggression in fruit flies almost as much as genes. So you can show that if you socially isolate flies, you just let one fly grow up from its pupa in a vial and then test its aggressiveness, those isolated flies are much more aggressive than flies that have been housed in groups. And this is also true throughout the animal kingdom. Socially isolated
So if you're
mice,
isolated, you're going to be more aggressive.
You're going to be more aggressive. This is a
that.
biological universe. That's right.
I'd like to show you a video really of what's cutting edge now in robotics and what's cutting edge now in human performance, just to give you a feel of how close we're getting. So if we could roll the video of the robot. What this video shows is an end of a 3-year project by my colleagues in Germany, teaching a robot to pick up a glass and pick up a jug of water and pour some water into a glass. And as you can see, it does the task, but clearly it's not doing it anywhere as fluidly or speedily as a human would do it. You would regard this as rather poor performance. So this is a very challenging task. And if you now want to train this robot to do something different, you'd be starting another 3-year project. There's no generalization from one task to another. So this is a fundamentally very difficult problem. Let's compare that now to what we regard perhaps as the cutting-edge human performance. So what we're going to see is a small child, I think a 9-year-old, winning the world record for cup stacking. Now, cup stacking is a popular sport in America. It involves taking, I think, 12 cups and stacking them and unstacking them in a particular sequence as fast as you can.
Wow.
So this is not sped up at all.
This is great.
We've got a very long way to go before we get anywhere near to be able to build machines or understand even how that child learned to do that task.
One of the greatest challenges for neuroscience today is to explain mental illness. Despite advances in psychotherapy and drug development, depression, bipolar disorder, and schizophrenia are still common. In our 9th episode of the Brain series, I spoke with 2 remarkable women. Kay Redfield Jamison, though bipolar, is a best-selling author, and respected brain researcher. Ellen Sachs, who has schizophrenia, is an author, a law professor, and a mental health advocate. They talked about their experiences with mental illness and how they have learned to manage their disease.
I think that one of the things that's hardest to explain to anyone who's not been depressed is how isolating it is, how painful it is, and that kind of pain just, I'm convinced, cannot be put into words. No matter how many great writers have tried to put these things into words, you simply cannot convey to anyone. When you think about illnesses like terminal cancer, where you would think people would be thinking of dying and committing suicide, the suicide rate is really quite low. The people who really tend to kill themselves are people when they're depressed. It is a level of agony, of arterial agony, that is just astonishing. And as I say, isolation, a sense of what's the point? You know, you don't feel human, you can't think, you can't feel, can't love.
And some people reach out for suicide.
Absolutely.
When did you know?
Well, I certainly knew. I first sort of flew quite high, as it were, when I was about 17 and a senior in high school. And I felt great. I felt no pain. I had a wonderful time, but it wasn't that different from my usual joie de vivre. So I certainly, other than noticing that my friends were dropping like flies from exhaustion, it didn't seem that bad. What then happened is that I crashed completely, and I had never been depressed a day in my life. I'd never thought about suicide a day in my life or a minute in my life. And all of a sudden, I was incapable of remembering anything, concentrating, reading anything at school, making sense of anything. And I just wanted to die. And I went around trying to figure out how I could die. I thought of death. I felt, and I knew something was very seriously wrong. But at that time, I didn't put in, nobody talked about depression. Nobody talked about bipolar illness or manic depressive illness. The words weren't there. So I didn't know what to do. So I did nothing.
Until?
Well, I kept on that way, up and down for another 10 years. And then I went flamingly psychotic. I was hallucinating and delusional and manic, spending a lot of money that I didn't have, and not wisely. And it was a medical emergency. So I was brought, to care, as it were. And I was very fortunate. I had a terrific psychiatrist who diagnosed what I had absolutely correctly immediately, and I responded very well to lithium.
When I try to explain to other people what a psychotic episode is like, unlike mania, which is fun, a psychotic episode is horrible, it's terrible, it's an enormous pain. And I say it's like a waking nightmare with all the bizarre images and impossible things happening and the utter terror. Only with a nightmare, you kind of sit up in bed and you wake up and you can't just open your eyes and make psychosis go away. So that's what it feels like. For myself, I will have prominent, bizarre delusions, like I've killed hundreds of thousands of people with my thoughts. I have occasional hallucinations, a big spider walking up a wall, Santa Claus coming out of a TV. Who knows what that was about? And I also have disorganized thinking. So I had a breakdown on the roof of the Yale Law School my first semester there, and I said to my classmates, are your legal cases being infiltrated? We have to case the joint. I don't believe in joints, but they do hold your body together. So loosely associated words that, when put together, don't really make sense. And that happens to me as well. I have been very fortunate that, except for the first 2 years of my illness, I have not had negative symptoms.
Now, are there phases for this?
There are different sort of what are called course indicators. So some people might have one episode and be fine. Some people are chronically psychotic. Some people have episodes with inter-episode being okay, which is where I fit in. Mm-hmm. And on my own kind of course of my illness, I kind of divided into different phases. And in the first phase, the kind of prodromal phase where things started going wrong, I had my first kind of florid psychotic episode. I started walking home from school in the middle of the day and felt like the houses were communicating with me. They were sending messages, you are special, you are especially bad, look, see, you must find. It was very scary. When I got to Oxford, I kind of officially broke down. And that's the second period. It started out looking like depression with mild paranoid features, but over time developed into more of a thought disorder than a mood disorder. And I was hospitalized the first year for a month, the second year for 4 months. By the second hospitalization, I was having really frank psychotic thoughts, like beings in the sky were putting thoughts in my head, commanding me to do things like walk under in the hospital tunnels underneath the hospital and hurt myself and things like that. Eventually they sent me to a psychoanalyst, which I think was a prescient idea that it would help me because it's been enormously helpful. And during that phase, I was not on medication. Two things happened. My psychotic symptoms got worse. The positive symptoms got worse. So I was like living in the land of psychosis maybe 80% of the time.
You mean this was during the analysis it got worse?
Yeah.
Yeah.
But the negative symptoms got better. I started being able to relate to people again and work again. And my own theory is through the mechanism of getting connected with the therapist, I started getting connected with other people too. Then I had a big breakdown in New Haven, got into analysis with another analyst and got on medication and had a big 10-year struggle with whether I needed medication. For me, my motto was the less medicine, the less effective. And the way I could prove I wasn't really ill was by getting off medication. So I undertook each effort with great gusto and failed miserably. Yeah. Eventually, I went to Los Angeles. I got a really great teaching job. And my analysts started saying, you know, you should just stay on the medication and get on with your life. And eventually, I tried that. And this is the fourth phase. Got on a great medication, first Zyprexa, then clozapine. My symptoms haven't gone away completely. My husband says psychosis is like an off-on switch and not like an off-on switch, but like a dimmer. So at the far end, I'll have a transient thought like I've killed people, which I immediately dismissed. Further along the continuum, I might spend 2 or 3 days in the land of psychosis. And at the very far end, I would be crouching in a corner shaking for 2 weeks. That hasn't happened in a decade.
In a decade.
Unfortunately, psychiatric illnesses such as depression and schizophrenia are not the only diseases that affect the brain and the nervous system. Neurological and neurodegenerative diseases like Parkinson's and stroke are all too common. While some of these diseases remain mysteries, others are on the verge of being cured. Our panelists talk about some cutting-edge treatments in this episode.
Here we have technology that allows us to peer into the brain. We have an understanding, at least a primitive understanding of what that part of the brain, the arm area of the motor cortex, is trying to do. We could, in fact, take people who are paralyzed, that is, able to think about movement but not able to move, and connect their brain back up to the outside world. So I guess what could be seen as a rather bold step, but we sought FDA approval, and we were approved by the FDA to study a small number of severely paralyzed people, tetraplegics, that can't move their arms and legs. And we implanted 5 people so far in this small trial. And I think just by illustration, I'll show you one of the first patients. His name is Matt Nagel. He's playing a video game here. He's supposed to hit those things those are treasure chests and avoid the squares, which are actually goblins. It's a video game called He-Man. So you'd say he was playing that video pretty well, but not great. But in fact, Matthew was injured in his cervical spinal cord. It completely disconnected his brain from his entire body. He has the chip in his arm area of motor cortex, and merely by thinking about moving, he's actually making that cursor move.
I just think this is stunning.
Amazing.
I mean, that you can.
Amazing.
But again, it's a true example of taking the information from basic science. We had all the pieces, and we just put it together so that we could reconnect the body to the outside world. We want to give a couple of examples that I think take us. So we've sort of stepwise gone through this. So one step is, can you control something physical? So we thought of something physical, a mechanical hand. So Matthew can't control his own hand, so we brought a mechanical hand. Right. And here we're seeing a video of Matthew thinking about opening and closing a hand, and there he is opening and closing his hand. It had a very profound effect on him because it was the first time in years that he had actually moved anything physically himself, but he's doing it entirely with his mind. Then to extrapolate that a bit further, we asked, well, could you control something practical like a wheelchair? This is actually a lady who has what's called a brainstem stroke. It's a little bit above the spinal cord. She's not only unable to move, she can't speak. But what she's doing here is using BrainGate, this chip, to control that wheelchair. So it's wirelessly beamed over to the wheelchair, and actually the control system is that little computer mounted on the wheelchair. And I had asked her to drive the wheelchair over to the door, and she had practiced for about 5 minutes before this. And here she is sort of not very gracefully, but driving it over towards the door, and you'll see it progress up over to the door. And of course, you know, the control isn't good enough. We wouldn't have her in the wheelchair. We just had her do it remotely. So at this point, we've shown in each of several different disorders, that includes spinal cord injury, in stroke, and even in 2 ALS patients, that's possible to decode the brain, sense the signals, decode the brain, and connect them to devices. But these are all demonstrations. We're not there yet where these are available for everyday use.
What is also so wonderful about this is not only the clinical effect, which is so dramatic, but it really shows that John has learned how to read the brain, how to use the information from the brain to drive a device. So that itself is a major insight, that you can make sense out of the action potential sequences in the brain. And it really brings us to John's aspirations here, John Krakauer, of what you hope to do with stroke. Why don't you outline for us your thinking about that?
Well, right. So I think it follows very nicely, because the very same plasticity in these extreme cases where you're disconnected, where you're going to have to bypass the severed pathways and control an external device with this plasticity. Well, in patients who have stroke, for example, where they still have some residual movement left, the question you want to ask is a similar one. Can you somehow augment their plasticity and sort of enhance their recovery? And so there are a number of points to make about that. Most patients after injury, that are less extreme than what we just saw, recover to some degree. And they recover most of the time within the first 3 months after stroke, but not completely. And we know from animal models that we were talking about before that this seems to be because of a time window of plasticity that finishes after about 3 months in humans. It's about 4 weeks in rodent models. So what we want to do is, can we use technology to try and take advantage of this period of plasticity in patients after stroke? So there are two kinds of technology that are being used increasingly now. So here is a Rio Go robot. This is basically a robotic device that attaches to the affected limb of a patient after stroke. And what this robot can do is it can give varying degrees of assistance to the patient, so that when they start to make a movement, the robot can give them 3D assistance. And as they get better, as they begin to understand the kind of movement required of them, you can begin to take away the robot's contribution. So the idea would be to take patients early after stroke, and with the use of a robot, which can give you hundreds, if not thousands, of repetitions, and we know that large amounts of practice are required to actually interact with this plasticity to get recovery. So what we need is some sort of device that doesn't get tired and can be programmed to give you hundreds of thousands of repetitions and do it early. And these are what these robots can do. The second kind is to do something non-invasive. Unlike what we just heard from John, in patients who are less severe, we don't necessarily think we have to put electrodes into the brain itself. We feel like we can actually stimulate motor cortex externally with either electrical or magnetic stimulation. So here in this slide you can see this figure-8 coil, and what you do is you put current through that coil, which then generates magnetic fields which are at right angles to the surface of the brain, and those magnetic fields induce current in neurons and stimulate a motor cortex. The other one, instead of using magnetic fields, you can use essentially a 12-volt battery over the head, and that also can actually increase excitability of motor cortex. And these are two ways to augment activity and plasticity over targeted areas of the brain, and a lot of studies now are showing that these can increase and improve performance. So the dream would be, the cocktail would be, to take a patient early after stroke in this window of plasticity, hook them up to a robot, and stimulate their brain at the same time, and potentially give them some sort of drug, and with this cocktail ramp up the amount of recovery that could occur in these patients early after stroke.
As the series drew to a close, we turn to topics that neuroscience is just beginning to address. Our 11th and 12th episodes covered decision-making and creativity. On the topic of creativity, the artists Chuck Close and Richard Serra explored how they see creativity and how it works for them.
I think, first of all, we have to understand what it is that drives decisions. So we have to understand the neural mechanisms and how they actually interact with each other. I mean, I was having exactly this conversation that you raised with an economist colleague of mine at Stanford recently, and the guy at Stanford is skeptical about the relevance of neuroscience for economics. And he said, you know, all I care is the choices that people make. I just care what happens in the end. I don't care what's going on in the brain to produce the choices. The choices are something I can measure. That's my data. That's what I work with. And I think my counterpoint to him was, you can measure the choices now, but how are you going to predict choices in the future in different situations? And the dominant model in economics right now that's used to explain choice is actually economic rationality. You know, that you choose the thing that actually is the best in the long run in terms of economic outcome. But we know people don't work that way. Kahneman and Tversky, who we've already talked about a little bit, know that we don't work that way. And so the question then is, what are the deeper underlying principles by which decisions get made? And if we can understand those, then we can predict behavior better. I mean, we've just come through a period in this country with disastrous economic decisions having been made. And disastrous kind of decisions being made at the levels of, you know, do we regulate, do we not regulate, what kinds of instruments are wise to use? And these are deep-rooted decisions that get made in human behavior, and that we need to try to understand where the decisions come from. And the rational model is not going to, in the end, be a very good guide.
I think a simple example of what neuroscience can offer is the realization that we've had from Freud and even before, how important emotion is to people's behavior. And your example, how sometimes emotional processes are recruited and sometimes they're not for decision-making, for moral decision-making. We need a direct measure of that. If we can image people and say, we recruit the amygdala under these circumstances, we don't recruit the amygdala under those circumstances, we have an independent way of evaluating under what circumstances emotional processes recruited. And I think that's extremely important, because otherwise we're just inferring that this is happening. This provides us a direct measurement.
Emotion is something we have a very difficult time studying in animals, actually. I mean, this is much more tractable in humans, one of the things that's much more tractable. And Ray sort of talked about this parliament of decisions and decision-making voices and sort of the higher-level reasoning and this rambunctious, bubbly kind of emotional substrate. And Josh mentioned emotion. And I know, and the question is sort of, is emotion something that's valuable and that we should be keeping, or is emotion sometimes that leads us astray in decision making, and how do you recognize one versus the other? Because sometimes emotions clearly lead us astray, and utilitarian calculus would discount emotion completely and just say it's a numbers game. But sometimes the emotion, the empathy, the ability to empathize with other people that the psychopaths lack is a good thing. How do we think about pluses and minuses of emotion?
So I think this is where I think that the camera analogy is very useful. If you think of the emotions as being like the automatic settings, and you think of manual mode as being like reasoning, you can ask of a photographer, well, what's better, the automatic settings or the manual mode? And what the photographer will say is different things are good for different circumstances. That if you're in a standard kind of photographic situation, the kind that the manufacturer of your camera could anticipate, then go ahead and use your automatic landscape setting or whatever it is. But if you're facing a fundamentally new kind of photographic challenge, then you're probably going to have to put your camera in manual mode. And so I think that what we really need to do as a society is understand ourselves so that we can know how to use our moral brains. Understand when we're dealing with the kind of situation that we've been well prepared for, either by our genes or by cultural influences or by our own experiences, and when we're sort of going out on a decision-making limb. An example of going out on a decision-making limb would be dealing with something like global warming. We have no genetic experience with dealing with global warming. We have no personal experience with it. I mean, we've never gone through a trial and error process because we're still on our first trial, and likewise for cultural ways of honing our decisions. And so in trying to come up with what's a fair way to divide up the burdens of solving this problem, should we go with historical emissions levels and say whatever's been in the past, that's more or less fair and we're going to stick with that? Or should we start with a clean slate and say every human on Earth has the equal right to emit carbon? Very different ways of looking at it. Obviously, different countries favor looking at it one way or the other. And I think our intuitions about justice and fairness may not be much help here. And we may have to put our cameras in manual mode and think like wonky economists. Other cases, for example, managing your personal life, it would be terrible to think like a wonky economist. And instead, you want to think like a poet. So we got to understand ourselves to use our minds better.
Creativity needs what?
I think for people who are making and doing, when you're actually making and doing something, you don't think, I'm creating. That's not how, at least I don't. I don't think, oh, now I'm creating. I think that certain aspects of what I would like to find out about my own experience in doing and making lead to develop certain processes that will allow me to have a certain feedback that will allow me to continue. When I first started in New York, I just wrote down a list of verbs. and I decided I would enact the verbs in relation to material, in relation to place, and in relation to sometimes even time. So I'd take very simple things, and I would either roll lead up or lift a piece of rubber up, and I would call them to roll, to lift, to hang, to bend, to tie, to dapple, to twist, or whatever. And I thought by just using a very simple transitive verb structure, it would allow me to enact processes and motor control in relation to material that would then allow me to proceed in a way that I didn't have to deal with the specifics of history. It would allow me to have an own intrinsic logic in relation to what I was doing, in relation to the perception of what was the residue of the activity. Now, that doesn't mean that all activities and their residue are going to create something that is satisfying in terms of what you would call an aesthetic experience. Most of them not. But every now and then you would have a moment where you would say, aha, I've done this, and this satisfies certain parameters of what I can then relate to in things that have been done before, but no precedent for it. And the very early work was a simple taking a piece of rubber about 4 feet wide and about 8 feet long, grabbing on its edge and just lifting it up, and it was called to lift. Once I stood that up, I realized that I could accept the topological continuousness of this form as a sculpture. Now, the immediate generation that had come before had dealt with the hierarchy of the object, and they weren't involved with the process of the material, and they had specific intentions. Well, I was more interested in my own physical experience than somebody else's intention. I wasn't interested in script. I was interested in how I could physically interact with material and what the residue would be in terms of anyone looking at it being able to reconstruct what had been done. Whether or not that was satisfying aesthetically for other people or not, at that point didn't concern me. And I was working with various people. I had a small trucking company, so it was myself, Chuck, Phil Glass, Bob Fiore, Michael Snow, Steve Reich. So there were a lot of painters, other sculptors, filmmakers, musicians who would help me. And there was a dialogue that went on between us that was involved with process, time, movement, place, that didn't really adhere to any discipline. So there was an interconnectedness in the language that we all shared, and there wasn't any competition about one outdoing the other because we were all involved with a similar language, which up to that point really hadn't hit the museums. We were doing the work for each other.
Does this resonate with you, Chuck?
Yeah, I remember being in Richard's studio when he says, "Look at this," and he reaches down, he lifts the thing up, and we're like, "Oh wow, this is really an amazing thing." But I think in terms of how we ended up doing what we're doing, I think there's a common misunderstanding about how generations of artists move away from other people's work. There's a commonly held belief that we're reacting against work that we find bankrupt, uninteresting, devoid of any value, and therefore you go out and make something else. I thought we loved all those people so much, and we thought we were going to be doomed to be followers if we continued to make work that looked like everyone else.
Our generation really wanted to create something that was not familiar. And I think to make something that is unfamiliar is actually probably to make something new and to create something. To make something familiar is to deal with facts that have come before. And in watching the segments of this programs, I didn't watch the last few, but I was struck that the passion of scientists trying to deal with something in relation to the given history of facts and then offering something new, I think is probably fairly consistent with how a lot of artists work.
Eric?
This is what struck me, and Anne also made this point. There must be a common sort of set of stages whereby people solve problems in what other people see.
I think problem solving is not the issue. I think that's problem creation is much more interesting.
Selecting what is the interesting problem.
I think what we did was try and find a way to back ourselves into our own individual corner and ask questions of ourselves that no one else's answers would fit. And then the search was on. But again, it was a choice not to do something. Ad Reinhardt was very important for me. I don't know if he was for you, but his writings were that he made the choice not to do something a positive decision. No more of this, no more of that. We're not going to do this anymore. We're not going to do that anymore. And I thought, oh my God, if I want to move, not necessarily progress, but if I want to move from where I am, I can construct a series of severe self-imposed limitations. If I'm going to, make something, then I'm going to say, I'm going to purge my work of virtuoso brushmanship. I'm going to try and get the artist's hand out of there. I'm going to limit myself to one color, just black paint on thin down on a white canvas. My hand wants to make art shapes, so I'll work from photographs, so the shapes have to be the shapes in the photograph. I'm plagued with indecision, and I paint it in, scrape it off, so I'm only going to work with one color, so that I'm forced to make decisions early and live with it. Purge the work of everything else.
Being an artist and a scientist both, is there a difference in scientific creativity and what we might call artistic creativity, for the lack of a better word?
Well, it's easy to argue both for the similarities and against them. A great physicist who was also a very fine amateur pianist has a chapter in his autobiography called Mozart and Quantum Mechanics. And he says that for him, when he's doing one or the other, they're profoundly different. I mean, for me, narrative, which is my medium, somehow seems to combine them all the while, or at least I hope it does.
I think the problem that Chuck and I may have with the word creativity is that seen from the outside, it seems like a very exalted term, and people, attribute various status symbols to it or whatever. Seen from the inside, it's probably an unending question mark, if not paranoia and
paranoia or
sublimation. And that's an interesting point I'd like to bring up. How does one account in science or in brain science for the activity of sublimation? Or is it accounted for? Because it certainly is apparent to me that, and I just gave a talk on Louise Bourgeois, who talked about it all her life, that her sexual drive was sublimated in her work. That was the manifestation of her work. Now, does sublimation play a role, or have they found, does it play a role in the synapses that occur in the brain?
I think there may be an interesting historical example with Herman Melville. Herman Melville wrote several very popular novels, Omu, Taipi, and so forth, in the 1840s. He was highly talented, but not particularly original. And then something happened around 1850. He fell in love. And in fact, he fell in love with Nathaniel Hawthorne. Oh. And this was not reciprocated. And therefore, the libido didn't have its normal outlet. And it was in this state of passion and restraint that Moby Dick emerged.
The human brain is an endless source of wonder and mystery. With each new discovery comes new possibilities and new questions. At the close of each episode of this series, I asked the panelists to tell me the one question they most wanted to be answered. Their responses were fascinating. Here are a few.
The question I'd most like to have the answer to is, how is it possible for a human brain to think an abstract thought? You've learned on this program, you've talked about how the brain only gets input from its perceptual systems, and it only affects the world through its action systems. But there are limits to what we can see, and there are limits to what we can do. But we can close our eyes and we can imagine a line that's infinitely long, a point that's infinitely small, a series of numbers that goes on forever. And our ability to imagine those things forms the basis of everything from formal mathematics to science to technology to everything that we are. I don't think we understand how the brain does that. I think for all the advances that have been made in genetics and neurobiology, we don't know where abstract ideas come from. But my hope is, if we could figure out how little kids get to have them, we might start making some progress.
I would like to know what the computations are that the visual system does in order to tell the difference between light and shadow, between light paint and dark paint. Just very simple things that seem trivially simple to us, but which apparently involve very sophisticated computations.
Is that a mathematical formula or something? Or
yes, well, someday we'll figure out what it is, but it is the way you take all these numbers that the eye is giving you, the light and dark and color. Yeah. How do you shuffle those numbers, recombine them into something sensible that tells you about what's in the world? That's the problem of sort of the theoretical problem of human vision, and it's the practical problem of computer vision.
I think we've been hearing a lot about fear, aggression. In other shows you've talked about vision or movement and so forth. And so we're very good in neuroscience at understanding how pieces of the brain work, or little components, little functions work. But what we don't have is an understanding of how the brain itself works. We need a theory of the entire brain and how, through this operation of the brain as a whole, our self or personality comes out of the brain. We have very little clue to that.
I'm very interested in understanding how we feel. There's no question that we have a pretty good idea of how we emote. And we have the basic idea of the circuitries that will permit us to create this portrayal of the body when it is having an emotion, and that's the feeling. But how exactly it works, we don't. And for example, why is it that a feeling feels like anything? Why is it that a feeling feels the way it does? Why is it that you can feel pain or we can feel pleasure? There are a number of unanswered questions there, and I think that, like with many other aspects of our minds, we're going to find the answers in neuroscience. We just need to have different approaches, but that's my main question right now.
I think one of the things that are lacking in areas that interest Jerry and me is the lack of progress in psychiatry. We really don't have any better drugs for treating schizophrenia than we had when I was a resident in 1960. Chlorpromazine has more side effects, but is as effective as anything that's come along. There's been no new antidepressant for the last 20 years.
Amazing.
And animal models of these disorders are coming along. They can be very useful. And it turns out that many mental illnesses have a memory component. Schizophrenia has a defect in the prefrontal cortex. People with schizophrenia don't organize their lives. And one can now develop animal models that have alterations in the genes that are thought to be involved in schizophrenia and see how they affect prefrontal cortical function, working memory tasks. One can do this with depression. So the combination of approaches, knowing which parts of the brain are involved, often identified by imaging or by physiological methods, putting this together with genetics does allow us to make progress. I think one has to realize that these are immense questions. You're asking the most profound questions Western thought has ever challenged. And we're not going to answer it immediately, but at least we're beginning to mass the troops, both intellectually and methodologically, to approach those problems.
Thank you for joining us. We hope you have enjoyed this journey as much as we have, and we hope that you will join us as we launch year 2 of our Brain series coming up this spring. Until then, see you next time.